Hi everyone, and welcome back to our YouTube channel. In today's lecture, I will cover one of the most fundamental topics that you may come across in any linear algebra course. And this topic is determinant. In this lecture, I will show you the definition of a determinant, and then we will compute the determinant of a given square matrix by using its definition itself. But before even to do so, we need to learn some terminology related to definition of a determinant. And this terminology has something to do with permutations. Alright then, having said that, let's first try to understand what a permutation is and what is the sign of a permutation. In other words, let's first define a permutation and then show you how to find the sign of a given permutation. Alright, and here is the actually basic definition. Suppose we are given n elements, and in our case, suppose we are given n positive integers from 1 to n. So say 1, 2, 3, blah blah blah, n. And actually, this ordering is called a permutation of this n elements. And a permutation is said to be any rearrangement of these n elements in some orderings. So what I mean is, for instance, if I take the value n is equal to 3, then what do I have? So say take n is equal to 3, or let n be equal to 3. Okay, so what I have is, if I write them in the natural order, we have 1, 2, 3, right? So we have this 3 tuple. And this is a permutation. Why? Because actually this is an arrangement of 3 elements. And by the way, this permutation is called a permutation that has a natural ordering. Why? Because when we look at this permutation from left hand side to the right hand side, they are ordered conventionally. So 1, 2, 3. And a permutation is if we rearrange these numbers. For instance, if I write something like this, 3, 2, and 1, and this is also a permutation, okay? Say this is permutation. Let's say P0. This permutation has a natural ordering. And say this is another permutation, P1, right? 3 to 1. How about writing another one? So a permutation is nothing but a rearrangement of these 3 elements when we take the, of course, value of n is equal to 3. So this is also a permutation. So I can switch the positions of these 3 elements in any order. Then that means I have another permutation. So one simple question before going on is that, for instance, if I take n is equal to 3, then how many different permutations should I have? So we have actually 3 positions, right? And in each position, I can use only one of these 3 elements. And I am not allowed to use any element twice or more. So only once. Each spot has only one number. So in the first position, I have 3 different options. And since I will be using one of these 3 elements, then in the second position, how many of them do I have? Now I have 2 different options. And for the last position, since I already have used 2 of them, I only have one position, one number left actually in this position. So how many different ways? So 3 times, 2 times, 1 for each position. Then in total, I have 6 different permutations when I take the value n is equal to 3. Okay, this is what a permutation is. So, in short, a permutation is a rearrangement of n elements. So when actually that means if I switch the positions of 2 elements, then I obtain another permutations, right? As long as I keep doing the same process, I will be producing other permutations. So this is the definition of permutation. And another important term related to permutation is that we have another definition, namely sign of a permutation. And what is the sign of a permutation? Let's suppose we show the sign of a permutation P like rho P, okay? So, and before even actually defining the sign, let's first make some observation. All right, now, suppose I have P2 here, and I want to somehow turn this permutation P2 into the P0. So how can I do that? What I need to do is actually, I need to switch the positions of some elements to convert P2 into P0, right? P0 is the permutation which has a natural ordering. That means in the usual order, 1, 2, 3, okay? So this is actually the base case for a permutation. And if we rearrange these elements in some other arbitrary order, then we have another rearrangement, which is called another permutation. All right, so let's get back to our point. So how many? Well, what I need to do is just, I need to swap the elements, right? So in other words, I need to perform some interchange operations to convert P2 into P0. And what this means is, so suppose I have 2, 3, 1, all right? So, and I want to restore P0 by using this permutation, namely P2. So what should I do? Well, in the first position I have 2, but in P0 I have 1 in the first position. So I can perform a swap operation here. So I can interchange the first and third position. So what do I have in this case? Now I have 1, 3, and 2. That's good. I get closer to the destination. So then, but I still actually need some more operation, right? So I have now 1, 3, 2. But what I need is 1, 2, 3. So I can interchange the second and third positions. So what do I have in this case? Now I have 1, 2, and 3. That's good. So we hit the target, right? So we have 1, 2, 3. We have the permutation that has the natural ordering. And how many interchange operations I have performed in the meantime? Well, 1 here and 1 here. So I have 2 interchange operations. So I apply 2 interchange operations to obtain the original ordering. All right. How about P1? What should I do? Now, assume that I want to restore P0 by using P1. So we have 3, 2, and 1 in the beginning, right? Then what should I do to have an ordering like 1, 2, 3? Well, it's simple. Only one interchange would be enough. If I swap the positions of the first and third element, then what I have? Now I have 1, 2, and 3. So that's good. So how many interchange or swap operations I have performed? Only one, right? So with one operation, I restored the naturally ordered permutation, which is P0 in this case, 1, 2, and 3. Okay, so what I'm trying to point out is, as you notice, guys, if I want to restore the permutation that has a natural ordering, I either perform even number of interchange operations between the elements, or I perform odd number of interchange operations between the elements of that permutation. And there is no other option, right? I will either perform an even number of operations, swap operations, or odd number of them. All right, now then come to another point. Now we can define what the sign of a permutation is. So say rho P is equal to, well, here this rho P means the sign of the permutation. Okay, so this is the sign of the permutation. Let's define what does it mean for a permutation to have a sign. Okay, sign of the permutation P. Okay, and this is equal to either +1 or -1. So a sign of a permutation has two different values, and they are either +1 or -1. And what is the definition? If the number of swap operations to restore the permutation that has a natural ordering is even number, if it is an even number, then it has the value +1. So if we perform even number of operations to restore the permutation that has a natural ordering, then its output is equal to +1. But if we have an odd number of operations, then its value is equal to -1. All right. Now, having said that, okay, so if you look at the example I have just given you above, so what can we say? For instance, if I want to write the sign of P1, then what is the sign of P1? So how many swap operations did I perform to convert P1 into P0? And the P0 is the permutation that has a natural ordering, right? I've just performed one interchange operation, so it is an odd number. And if it is an odd number, then its sign is equal to -1. How about P2? So for the permutation, namely P2, I performed two interchange operations, right? As shown above here. So which means I performed even number of operations to restore the original permutation. And since it is an even number, then the sign of P2 is equal to +1. Alright guys, now we know what a permutation is, and we know how to find the sign of a permutation. Now we are ready to define what a determinant is. Alright, let's define the determinant of a given square matrix. Right. So we now have the basic terminology in order to understand the definition of a determinant, because the definition of the determinant is completely related to a permutation and its sign. Okay, here's the definition of the determinant for a given square matrix. Well, first of all, let A, here's a matrix, but A is an n by n matrix, so this must be satisfied. So we need to have a square matrix to define the determinant, or to find the determinant of a matrix. First of all, let A and n be a square matrix. Okay, so we have a square matrix here, and right, square matrix, and following that fact, we can define the determinant of a matrix, which we can show that A, which represents actually determinant, or like this, right? We can show the determinant in the symbol with this vertical bars on both sides, which reminds you the absolute value, but don't forget we are now dealing with matrices, so this is not the absolute value. This is the determinant of a matrix. So, and here is the definition. Determinant of a given square matrix is equal to the summation over permutations, right? P represents the permutations, unless otherwise stated. And this summation, well, this summation, let's write it. Rho P is the sign of the permutation, times some multiplication of the elements of the matrix in this form, say A1 P1, A2 P2, and multiplied by A n Pn, where this Pi values is the components of the permutation. So P is equal to P1, P2, blah blah blah, Pn. So Pi values are the components or the entries of the permutation P, and rho P is the sign of this permutation, and these Aij values are the components of the matrix, right? They are just the entries in the matrix with respect to these indices that we will find. Alright, and that's the definition of a determinant for a given square matrix. In other words, before giving you an example, let's first understand what a determinant is. This means, guys, if we are given a matrix, first of all, to find a determinant, this matrix should be a square matrix. What this means is the number of rows must be equal to the number of columns in this matrix. So that's why we call it as a square matrix. And only in this case we're able to find a determinant. And to find a determinant, actually, what should I do? Well, let's see how we can do that. How we can apply this definition. Let's give an example. Here's the example. Let's start with a simple case. So suppose we are given a 2 by 2 matrix, right? So let's start with a simple case and then continue with a more complicated one. Okay, let's produce some values, say 3, 2, 1, and say 3. Okay, now suppose this is the matrix whose determinant we try to find by using the definition of the determinant. Okay, if A is equal to this matrix, and by the way, as you notice, this is a square matrix, right? We have 2 rows and we have 2 columns. So the number of rows and the number of columns are equal. So since we have a square matrix, now we can start trying to compute the determinant. And what should I do? Okay, the question is find the determinant, alright? Okay, what is the determinant? Okay, but in this example, actually, I will find the determinant of this 2 by 2 matrix by using the definition of the determinant. In our future lectures, I will show you some other methods to compute the determinant. But starting with the definition is very important for us, because we will not only produce some formulas, but also we will make some key observations before proceeding with the more advanced techniques to find the determinant of a given square matrix. Alright, now let's apply the definition. Let's see how it works. Solution. Alright guys, the first thing to notice that we have a 2 by 2 matrix. And that means our permutation, let's say it P, has 2 elements. 1, 2, right? So this is our permutation, which is a natural ordering, a kind of base permutation that we will use to convert all the other permutations into this one. Alright, and since we have 2 elements, how many different permutations we have? So for the first position, we have either 1 or 2. And for the second position, again, we either have 2 or 1. So we have only 2 options. That's good. So we don't have so many permutations, right? So we have only say P1 is equal to 1, 2, and P2 is equal to what? We just swap the positions of the elements in the first permutation, right? We also have 2, 1. So these are the permutations. Now this is something that we need to find first of all. And what else we need to find? Well, what we need to find is we now need to find their sign, right? Because we look at the definition of the determinant, guys. What do I need to compute the determinant? By using the definition, all right? As you notice, let's use a red color. So if I circle in red, I need to find the sign of each different permutation, and I also need to compute this multiplication with respect to both the components of the permutations and the matrix. And then I will multiply the sign with this multiplication. Okay, let's see how it works. So let's find the sign. And what is the sign? So for the first permutation, we have P1 is equal to 1, 2. Then how many interchange operations should I perform to restore this permutation itself? So we are already at that permutation, right? We don't need to perform any swap operations for the first one. So I need to perform 0 number of interchange operations. So that means since I have to perform 0 operations, that means 0 is an even number, and since it is an even number, our sign is equal to +1 for the first permutation. And how about for the second permutation? Well, we have 2, 1. What should I do? How can I convert this permutation into the permutation P1, which has a natural ordering? Well, that's very simple. Just one swap operation. What I need to do is just I swap the first and second positions. So what I have in this case, I have 1, 2, right? So I restored P1. So only one operations would be enough. And since we perform odd number of operations, then what is the sign for this permutation? And the sign is equal to -1, since we perform odd number of operations. All right, let's continue. Now what am I going to do? Right? Now we should compute some multiplication, guys, right? So here, so what do I have? So let's write that. So A1, let's apply the formula P1. Okay, so I look at P1. So we have P1 and P2, right? So for the first permutation, what is the value of P1? And P1 and P2 actually are the values in the permutations. The first value, well, I count from left side to the right hand side. So the first one is P1 and second one P2 and P3 and so on, if we had more. Okay, so P1 is 1, and so we have A11 times, and P2 is 2, so we have A22, and we don't have any more because we have a 2 by 2 matrix, right? So in the last column, you see here, for the multiplication part, I use both the elements from the permutations and the matrix. So we have A11 times A22. And what this means? And what are these values? A11 and A22, actually, the values in the last column correspond to the entries in the matrix. And A11 is what? A11 is equal to 3, right? So what is the value of A22 in the matrix? In the original matrix A. So this is 3. So these are the elements that lie on the principal diagonal, right? If we draw this line, as you remember, this is the principal or main diagonal. So we have, so what is the result? We have 3 times 3. So which is equal to 9. Okay. Well, actually, let me write it right here. So actually, how did I find this value? A11 times A22, right? A22, right? That's the value. Okay, let's continue. How about the second permutation? Now, again, I apply the formula. What do I have here? I perform the formula in the definition. We have 1, right? A1, P1. What's the P1 value for the second permutation? We have 2 here, right? So this is A1, 2 times A2, P2. So what is the value of P2? We have 1 here in the second permutation, right? The second value in the second permutation is equal to 1. So I just write that. So these are the entries that we need to multiply with respect to the given matrix. A12 times A21. So what are these values? And now A12 is 2, right? So I just write its value. 2 times. And what is the value of A21? And this is 1, right? I just put the value here. So we have 2 here. How about the result? Alright, now I find the permutations. Since we have a 2 by 2 matrix, then we have 2 elements in the permutation, in each permutation, and we have 2 factorial, actually different permutations, and in this case we have only 2 permutations. And I found the permutations, and then I determine what their sign is, right? Depending on how many different operations would be enough to restore the original one. And by saying original one, I mean the permutation that has a natural ordering in the conventional orders. So it's just like 1, 2, 3 and go on. Okay, and then I compute the multiplication, but I'm not done yet. Then what I need to do is I also multiply the sign with the result of this multiplications, right? So this part is the third column, but the result is we have plus 1 times 9, right, which is equal to 9, and also we have minus 1 times 2, which is equal to minus 2, and due to the formula you see we have a summation here over the permutations, right? We have a summation, so we need to sum up these values. We need to sum up the final values, which means 9 minus 2, which is equal to 7. And we obtain the determinant of this given matrix. Alright, now, regardless of what matrix is given, as long as the size of this matrix is 2 by 2, actually we produced some formula with this definition, right? By using this definition, we actually have some kind of formula right now. In other words, if we are given a 2 by 2 matrix, then what is the value of the determinant? If you notice, no matter what values are given in this 2 by 2 matrix, well, actually we multiply the entries that lie on the main diagonal or the principal diagonal, and then we subtract this summation from the multiplication on the non-diagonal elements, right? On the non-main diagonal elements, which are 2 and 1 for this matrix. So if I want to formulate what I found in this example is something like this. So if we are given a generic matrix in the form of A, B, C, D, and this A, B, C, D's can take on any real values, okay, then the determinant of this 2 by 2 matrix is, okay, determinant, and let's give a name also, say A is equal to A, B, C, D, then the determinant A is equal to A times D minus B times C, right? So we just multiply the entries on the main diagonal and then subtract them from the result of the multiplication of the other non-main diagonal elements. That's what we need to do if we are given a 2 by 2 matrix. Alright, so that doesn't matter what the values are. Now we know how to compute the determinant of a given 2 by 2 matrix by using its definition. Okay, let's proceed with a more complex one. Let's show an example for a 3 by 3 matrix. Another example, okay. And use the definition to find the determinant of this 3 by 3 matrix as well. Okay. Now, say our matrix is this time 1, 1, 2, okay, 0, 1, 0, and 2, 0, say 3. Okay. Now let B given like this. So we have a 3 by 3 matrix this time. We have 3 rows and 3 columns. That means we have a square matrix, and therefore we are able to compute the determinant. And what is asked here is, of course, what is the determinant of B? And we are required to find the determinant value of this matrix by only using the definition of the determinant. Okay, let's solve this problem. Let's look at the solution. So what should I do? Now we have a 3 by 3 matrix. This means now I have 3 elements for each permutation, right? So my permutation, which has a natural ordering, has the form 1, 2, and 3, right? So this is the first permutation. And now how about now how about the other ones? How many different permutations will I have? Since I have 3 elements here, so we have 3 positions. And that means, okay, again, say we have 3 positions here. In the first position I have 3 independent different options, and since one of them is used in the first position, now for the second position I have 2 options, and 2 of them are used now, so I have 1 option for the third one. So when I multiply these numbers, I have the different possibilities. So I have 3 times 2 times 1 different combinations, so I have only 6 permutations. If I have, and this is actually called, when we multiply the integers from starting with 1 up to n, for this case n is equal to 3, then we have n factorial elements, right? So in this case actually this is the value of 3 factorial, and we use exclamation mark to represent the factorial, and this means 3 factorial means actually 3 times 2 times 1. So it is the multiplication of the integers starting with 1 up to that number. So if we have n factorial, that means we need to compute the multiplication of the numbers from 1 to blah 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 up to n. Okay, this is the definition of n factorial. Okay, since we have a 3 by 3 matrix, now we have 3 factorial permutations. So each permutation must have 3 elements. And how about the other permutations? Okay, I will just find all the other 5 possibilities, and if we keep the first position and just change the last 2 positions, then what we have? So let's give some numbers, of course, P1, P2, to avoid confusion. So we have 1, 3, 2, right? This is another ordering. And now say P3, okay? And what's the P3? Say this time it's 2, 1, 3, and let's say P4. And what is the value for P4? Okay, I just write a different permutation now. We have 2, 3, and 1. Okay, and how about the last 2 ones? Say P5. Okay, now let's put the value 3 in the first position and swap other elements, right? 1 and 2 between themselves. Okay, 3, 1, 2. And how about the last one? Okay, there is only one more left. So now this is 3, 2, and 1. And these are all the permutations, right? We can find. So this is the first one. This is the second one. Third one. Fourth one. Fifth one. And the last one. Sixth one. Okay. Now, what should I do? Okay, now I need to find the sign of each permutation, guys. So I need to find the sign, right? So what are the signs of these permutations? Say row p values. They are either +1 or -1, depending on the number of actually operations. And this even or odd numbers of operations for this permutations are also called parity of the permutation. It's even parity or odd parity. So we will check it. Alright, now for the first one. Again, this is the permutation, which is a natural ordering. So 0 interchange. So no interchange here. That means since 0 is an even number and the sign is equal to what? Equal to +1, right? Okay. Let's extend these lines. I will need them in the following step, where I will find the result of the multiplication of the entries with respect to both permutations and the matrix components. Okay, how about 1, 3, 2? Alright, I look at P2, and as you notice, if I switch the second and the third positions, then I will restore P1, so only one change would be enough, which is an odd number, so this sign is equal to -1. How about for the third one? Okay, as you notice, it is 2, 1, 3. The third position is the same with the P1, but first and second positions are different, so only one interchange would be enough. If I swap 2 and 1, I convert P3 into P1, so one operation would be enough, and 1 is an odd number, so the sign is -1. How about for P4? Well, for P4, let's look at P4, what we have. We have 2, 3, 1. All positions are different, you see. Well, let's look into that. This is a little more complicated. Okay, let's write it here somewhere here. So okay, so we have 2, 3, 1. Okay, if we interchange the first and second positions, now what we have 3, 2, and 1. Now 2 is in its place, right? What is different is 3 and 1, and I can perform one more interchange. I switch the places of 1 and 3, and then what I have 1, 2, 3. So I reached my desired goal. How many operations have I performed in the meanwhile? Well, 2 operations, and 2 is an even number, and since 2 is an even number, then what is the sign of P4? It is +1. So that's as simple as that. Okay, how about P5? So we have 3, 1, and 2. And again, all the positions are different. Let's interchange the first and second one. So now we have 1, 3, 2. But it still doesn't have the natural ordering. What I need to do is just interchange 2 and 3. So now I have 1, 2, 3. And again, it takes 2 steps, right, to restore the original naturally ordered one. So 2 is an even number, and we have the sign +1. And how about the last one? Well, only 1 and 3. Okay, if we interchange 1 and 3, we have the desired output. So only one interchange would be enough for P6. Since 1 is an odd number and the sign is equal to -1. Alright. Now, again, Let's remember the definition, guys. Okay. Now the third column corresponds to the multiplication of the entries, right? So I will write these entries here. So for the first one, what do I have? So I have a 1, 1, and a 2, 2, and a 3, 3. I just put the values in the formula. So here in the formula of the definition, or in the definition actually of the determinant, we have P1, P2, Pn, and what these values correspond to. They correspond to the values in the permutation. So here in the first permutation P1, actually P1 is 1, P2 is 2, and P3 is 3. These are just positions actually, right? These are the elements that corresponds to that positions. So in the first column, what we have is actually the multiplication of the principal diagonal entries. So a11 times a22, and what is the value? This is 1, this is 1, and this is 3. So 1 times 3. So this is equal to 3. And for the last step, so what do? I multiply 3 by its sign, right? And its sign plus 1. So we have 3 for the first column. Now let's proceed to the second column. What do I have here? So again, I put the definition here. A1 and P1 is 1 for the second permutation. And A2 times P2 is what? P2 is 3, right? I just read the values in the permutations from left to right hand side to decide what the values of P1, P2, and P3 are with respect to the definition of the determinant. So we have now 2P2, and P2 is 3, right? I put it here. So we have also A3, and P3 is 2 for the second permutation. So let's look at the values. A11 is 1 in the matrix. Okay, these are the components of the matrix. So A11 means the element that is placed at the intersection of the first row and first column, and A23 means we are looking for the element that lies at the intersection of the second row and third column. So we look at the 2, 3 component, which is 0, right? This is 0 times, well, actually from now on it would be very easy. If we find a 0 value in this multiplication, I don't need to find the other values, right? Because multiplying anything else by 0 will yield us a 0 value. So we don't need to even look at the remaining values, but for the of course computational reasons, let's just write them. So A32 is equal to what? It's again 0. So this multiplication is equal to 0. And 0 times minus 1, don't forget to multiply 0 by its sign. And 0 times minus 1, again a 0, right? Let's continue. Okay, now A1, what is P1 here? P1 is 2, right? I read the symbols from left to right. So P1 is 2. So A2, 1 times A3, 3, right? So what is the value here in this case? Okay, A12 is 1 times A21. A21 is equal to 0. That's good. It just makes the computational process easier, right? As soon as we run into a value 0, then the multiplication would be equal to 0, because multiplying 0 by any real number will give us a value of 0 again. So, and then 3, 3, so this is equal to 3, but the multiplication is equal to 0. And don't forget to multiply it by its sign, but since this is a 0, that wouldn't change the result, but just be careful about it. So we have 0 here again. How about the other one? Well, I do the same thing. I put 1, okay, what's the P1 here? P1 is 2, right? A1, 2, and A2, 3, and A3, 1. Okay, so what are these values? A12 is equal to 1, A23 is equal to 0 again, and A31 is equal to 2, but this is also 0. Multiplying this value by its sign will yield us a 0 again. So if we have more zeros, then our computation would be easier. That's the only advantage actually, right? So that's the only advantage. Okay, continue. Now what we have? A1, 3, right? P1 is 3, P2 is 1, and P3 is 2 here. So A2, 1, and A3, 2. So the result is, okay, A1, 3 is 2, A2, 1 is 0, and A3, 2 is 0 again. So we have one more 0 here. So that's good. Okay, and multiplying it by its sign again as 0. And for the last permutation, do the same thing. We have A1, 3. We have A2, 2. And we have A3, 1. So what we have here, A1, 3 is equal to 2 times A2, 2 is equal to 1 times A3, 1 is equal to 2. Alright, now we have a non-zero element here, right? If you notice, now 2 times 1 times 2 is equal to what? It's equal to 4. But don't forget to multiply it by its sign. So 4 times minus 1, we have minus 4, guys. So now there is only one thing left to me to finish this computation. What I should do is I will sum these values up, right? So 3 plus 0 plus 0, 0, 0, and minus 4. And we have minus 1 in total. So the determinant of this matrix is equal to minus 1. So our result is determinant B is equal to minus 1. So by using the definition of the determinant, we have found the value of this given square matrix. Alright guys, I guess you enjoyed this video and you understand what a permutation is and how we can find the sign of a permutation. Okay, let's recap this lecture. So we start with a permutation. And what is a permutation? Given n elements, a permutation is nothing but a rearrangement of this n elements in some arbitrary ordering. And in our case, we order them in our convention from 1 to n, right? With respect to their numerical values. And we can perform some interchange operations to convert all other permutations into the permutation which has a natural ordering. And if this number of operations is an even number, then the sign of the permutation is plus 1. But if the number of these interchange operations is an odd number, then the sign of the permutation is minus 1. Okay. And the determinant is, well, actually the definition of determinant is directly related to this concept of permutation and its sign, because we take the summation over permutations to compute the determinant in this formula. So we just multiply the sign of each permutation by the multiplication of the corresponding entries. And that means, given a square matrix, we first find how many different permutations we have depending on the size of the matrix. In other words, if we have a 2 by 2 matrix, then our permutation includes 2 elements, and therefore we have 2 factorial different permutations. But if we have 3 by 3 matrix, then our permutation, each permutation actually involves 3 elements. That means we have 3 factorial, in other words 6 different permutations. And then we compute or determine the sign of each permutations by just looking at their interchange operations. So in other words, pick any permutation and try to convert it into the permutation that has a natural ordering and count the number of interchange operations, and if this is an even number, then the sign is +1, but if this is an odd number, then the sign is -1. And then by applying the definition here, a1 p2 a2 p2 and a1 p1 a2 p2 and blah blah an pn, depending on the size, and represents the size here, size of both the permutation and the matrix. So if you have an n by n matrix, we have n elements for each permutation, right? So we have n factorial different permutations in this case. For the 2 by 2 case, then we actually produce a formula. So if we are given a 2 by 2 matrix in the form of A, B, C, D as shown here, then what we need to do is just we need to multiply the principal elements and then subtract this result from the non-principal diagonal elements, right? AD minus BC would yield us the determinant of this 2 by 2 matrix. And if I perform the same definition for a 3 by 3 case, again I find all the different permutations along with their signs, and then I computed the multiplications, results of these multiplications actually with respect to both the permutations and the components of the matrix, and then sum them up to apply the definition of the determinant and find the result, and this summation will yield us the determinant. Okay, and before completing this lecture, actually, as the size increases, you notice that the number of permutations and the number of multiplications will also increase. So if we are given for instance, a matrix which is of size 4 by 4, then what this means? Then if you want to compute the determinant of this matrix, okay, say A is a given matrix, a given square matrix, which is of size 4 by 4, then, well, whereas to find the determinant of A, then how many different permutations we need to find? Well, first of all, we have, you see, 4 by 4 matrix. That means each permutation has 4 elements, and the very first one is 1, 2, 3, and 4, right? The permutation which is a natural ordering. And since we have 4 elements for this permutation, then we have 4 factorial different permutations, which is equal to 4 times, 3 times, 2 times, 1, and which is actually equal to 24 in total. And that means we need to first find the 24 different permutations along with their signs, and then with respect to these values also, by making use of the components of the matrix and permutations, we need to compute all the multiplications and then sum them up. And this really requires a heavy computational task for us. And even worse, if the size increases, if we have n by n matrix, right? So how many different combinations, or well, actually say how many different permutations we have? We have n factorial different rearrangements, right? So we need to find them, we need to compute their signs, and it is kind of difficult. But to understand the definition is very important for us, because when we make use of some other advanced techniques or some more convenient or easier techniques, we will understand what we really try to find if we understand what the definition is saying us, okay? And, well, of course, we need some additional techniques to make our computations easier. Alright guys, and there are actually some other methods that I will teach you in the future videos following this lecture, but in the next lecture I will also make some observations based upon this definition, and these observations would be really important for us to keep in mind. Alright, that's it for this course, and see you in the next lecture, and until then, have fun!